So, in a general sense, what the concentration of a solution is it is how much or the amount of our solute that is dissolved in the solvent or in the solution. So we're talking about how much solute is present in our solution. So we're going to be talking about in our units of concentration. Now there is a wide range of units for concentration depending on the area of chemistry or other parts of science or medicine. There's different units for concentration, but we're going to be focusing on two: percent concentration and molarity. But before we get into the mathematical parts, the numbers part or quantitative part of concentration, I wanted to look at the qualitative words that we might use to describe concentration. So when we have a small amount of our dissolved solute, we call that dilute. So a dilute concentration would have a small amount of your solute in your solution. And then if it's concentrated, that word would indicate that we have a large amount of the solute dissolved in our solution. So I always think of the example of a lot of household cleaning supplies now come concentrated. So if they're concentrated, it means that there's a large amount of the solute or the active ingredient or whatever you're paying for that is dissolved in that particular solution. And oftentimes when things are concentrated that we purchase, we end up diluting them. And if you were in class, I'd ask you how, but we add water to the concentrated part to make them dilute. So we reduce the amount of the active ingredient. And I think probably it's more cost effective, and it definitely requires less packaging when you buy things that are concentrated because they come in smaller containers and then we add our water. And I always think about this like in terms of household things. The word dilute and concentrated are totally fine. Like if I read the back of the floor cleaner I have, it says add a capful and then add up to whatever 5 gallons or 3 gallons. I can't remember, maybe 1 gallon. I don't even remember, because this is why when I clean, I throw a capful in and then I add water till it looks like the right bubbly that I remembered the first time. So I don't even pay that much attention. Not too many consequences. If I don't dilute it enough, my floor might feel kind of tacky or sticky. If I dilute it too much, then probably I'm not getting a very good clean from that. So that's the results. But when you think about in industry and medicine and other things that we would encounter, qualitative words are not really going to work. So we do want to know what it means in terms of solute when something's described as dilute or concentrated. But those are not going to be very helpful words in the sense of when we have to work in a laboratory situation. So we're going to look in this video at percent concentrations. I separated percent concentrations from molarity. So there's a separate video for molarity. So here are the 3 equations that we could use for percent concentrations. While your textbook has some other like parts per million and parts per billion, it might even have molality, I can't remember. I chose the 2 I chose because percent concentrations is really a unit that while we don't use in lab that often, it's really used in just in everyday life kind of things of commercial products. So things like alcohol, things like vinegars, like vanilla and those kind of extracts, mouthwashes, anything like skin creams with active ingredients, A lot of things that we buy commercially use percent concentrations as their concentration unit. So I thought, okay, I'm going to do that one. So it has 3 equations, and at first it looks so intimidating, but if you look at it, really it's 3 equations with only one equation, with only slight variation. So if we look, we can compare weight to weight. That's the first one. And notice weight, they're referring to mass. In fact, sometimes instead of using the word weight, some textbooks use the word mass. So if you're going online and looking for practice problems or someone else to explain it to you, it could also be shown up. It could also show as mass. So we can compare weight to volume. We could compare volume to volume. You see, that's the second one. And then weight to weight. And so everywhere we see weight, we're going to be using the mass, either of the solution or of the solute, and this always has to be in grams. So that's for our percent concentrations. And so we need that to be in grams. And then where you see V, that's the volume, and our unit that we're going to use is going to be in milliliters. So if they give you a unit in percent concentration that's in liters, for example, to plug it into this equation, you would want to convert it. So that's one thing we have to remember. So we're comparing different things, but if you look at what's the same, so I want to highlight. So look, every single one of them, oh, that's too dark of a highlight. Let me get a different one. Okay, I don't want to block out the word. Okay, so solute over solution, solute over solution, solute over solution. So every single time we're comparing how much solute we have in our solution. Right? So every single time. So the only thing that's changing is whether the problem's asking us to compare weight or volume. Okay, and then the other thing that they all have in common would be that they're all times 100 because every single one of these is a percent. So I don't give you these equations on the exam. So you have the choice of learning them, or you could use this on your card. This could be one of the things you write on the card if you would like to. But what I want you to encourage you to remember is it's always solute over solution times 100. And so the only thing that's going to be different is whether they're asking you to compare the masses or the volumes. And then what you have to keep in mind is if your mass, it's in grams and volumes in milliliters. So now I have several example problems that I want to do using these equations. All right. So this, and it says mass percent on the top, but let's pretend like this problem, we didn't know that. So it says, okay, calculate the mass percent of sodium chloride in a solution prepared by dissolving 50 grams of NaCl in 50 grams of water. Okay, so mass percent is a little odd this way, and you have to remember it. So mass percent, let's write the equation. That is going to be the weight over weight. So mass percent means you're comparing the masses. So that means we're going to have the grams of our solute, the mass, divided by the grams of our solution, because it's mass percent, times 100. Now, the grams of the solute is very straightforward. It's sodium chloride, so it's 50 grams. And there's not really any units here. I'll show you how they do the units. And then grams of solution. So here's the trick. The solution really is equal to the solute plus the solvent. And in mass percent, they often separate the two. So in this case, they gave us the 50 grams of sodium chloride, that's the solute, and then 150 grams of water. So that is the solvent, right? The solution would be both of those together, and they would use the word solution. So let's solve this problem, and then I want to relate it to your lab. Okay, so that's 50 grams divided by 200, because 50 plus 150 is 200, then times 100. So I get 25. My calculator just gave me 25, but I think I should have 3 significant figures. So 25%. And then what they would do is put, like behind it or sometimes in front of the percent, weight over weight. They could say percent by mass, or I could even see them saying percent M over M. So they don't include units here, but they'll tell you that the percent is by mass, which means it's comparing the grams of both. Now, I want to relate this to what you did in lab. In lab, we evaporated the solvent, water, off, and we had our dry salt. So you should have a measurement for dry salt. That would be your solute. Now, the grams of the solution, you don't have to add. Okay, so the grams of the solution you measured before you started boiling, right? You measured the evaporating dish with the solution in it. So if you subtract the evaporating dish, you have the mass of your solution. So in lab, you measured directly the mass of the solution. So you will not need to add your sodium chloride to it because you measured the mass of the solution. Okay, so you do not have to add the 2 at the bottom in lab. But in this homework problem or this example problem, which I know there's probably one in your homework too, they have it separated, right? They have the sodium chloride, which is your solute, and the water, which is your solvent, not your solution. So in mass percent, when they separate the solute and the solvent and give you both, you have to add the denominator together. Okay, that's something that you need to make a note, maybe like highlight it or something for mass percent so you can remember, because it's the only one you do it in. Okay, the only one. So that's one problem, mass percent. So now let's look at volume percent. So volume percent, let's read the problem like it doesn't have a title. It says a solution is prepared by mixing 20 milliliters of propanol with enough water to produce 400 milliliters of solution. What is the volume percent? Okay, so volume percent is when you compare the volume of the solute to the volume of the solution. So it's going to be the milliliters of the solute divided by the milliliters of the solution, because it's volume to volume, times 100. Now notice, and I highlighted it as I was reading it, in this problem, they don't say how much water you have. They tell you the total amount of solution. It tells you they added water, but they don't tell you how much. Instead, they tell you the total amount. Okay, so here's just a little side note. I'll get back to the problem. Masses are additive, which means that I can measure multiple masses, and when I put them all together, they would add. Volumes are not additive. So what happens when you're mixing 2 liquids is that sometimes when you mix them, the particles get closer together when they're mixed. Or I suppose they could even get a little farther apart. I've actually done a lab on it, and now I can't remember, but they don't add up Like it's not just like, oh, if I had 10 milliliters of water and 10 milliliters of isopropanol, that I would end up with a total of 20 milliliters. You don't. The molecules can get closer together, so you end up with usually less. Although I'm thinking this is when I worked in Arizona and we had a lab that we had to do this, and I haven't done it since, and that's been a long time, people, 30 plus years. So, and I'm trying to remember, it could be different with different liquids. In fact, my inclination is to remember that's true. But I just want you to know, masses are additive. That's why in the previous problem, we can add those masses, that's fine. But volumes, when you mix liquids, their volumes are not additive. So instead of doing that, they say, okay, we added enough water till we got to the volume that we wanted the final volume to be. Okay, so when you have liquids, they're never going to say the amount of water and the amount of solute and add those together. They're always going to say, oh, this is how much solution. So we don't need to add anything together. They told us the solution. Okay. The only one we need to add together is for mass percent. And I'm emphasizing this because this is a common mistake that people make on homework and on exams. So I'm just trying to emphasize it. So this is pretty straightforward, right? The one back to the problem. We know we have 20 milliliters of propanol, and we added enough water that we have 400 milliliters of solution. Don't forget times 100. So 20 divided by 400 times 100 times 100 is 5. Now, I just get 5 on my calculator, but I want 3 significant figures so I can add the zeros after the decimal. And so this is a volume to volume percent. You could also say percent by volume. Either way would be something we could see. Okay, so that's pretty straightforward. The difference here is they gave us the solution. We didn't have to add. And then the third equation is mass percent. So this is a little different. Okay, so I am not asking the calculation of the concentration. Instead, I'm asking a different component. So let's read. It says, what volume? Okay, so that's what I'm having to find. Of a 3% mass to volume hydrogen peroxide. So this is the concentration. Will contain 10 grams of hydrogen peroxide. This is the solute. So what I have to find out is the volume of the solution. Now I'm going to show you 2 ways. The first way is just plugging into the equation and solving algebraically. The second way is using concentration as a conversion factor. I'll talk about that when I get there. Okay, so here we're going to plug, this is the first way. Okay, so the equation is percent mass to volume is going to equal mass on the top. So it's the grams of the solute divided by the milliliters of the solution, because it's volume on the bottom, times 100. Okay, so what I don't know is that. I have no number. They want to know the volume of the solution. So I know the percent concentration is 3. I'm going to plug that number there. I know I have 10 grams of the solute. I'm going to put V for volume because I don't know that, and then times 100. So remember, when you have your unknown in the denominator, you're going to multiply it over to the other side. So I'd have V times 3. That's times 3 equals, I still have the 10 on top, times 100. Don't miss that 100. Sometimes in the a solution, it gets kind of dropped, don't miss it, okay? And so you could simplify here. If it were myself, I could see, all right, for volume, if I had the 10 times 100 on top, I would divide the 3 over. So I say 10 times 100 divided by 3. And I get 333.333, it's milliliters. I feel like 2 units is what I'm going to get, 2 significant figures because the 3.0%. So I would report 330 milliliters. So 330 milliliters of this 3% hydrogen peroxide has 10 grams. Okay, so that's how you plug into the equation. Now I want to show you, as a side note, how to use the concentration as a conversion factor. And I'm going to have to skip past the problem and go to a blank page. So I know my concentration from the other page is 3%. And I know the mass of my solute is 10. Okay. So, I don't know, now it's probably been it has to be more than 5 years, but many years ago, one of my textbooks really emphasized using concentration as a conversion factor, and I really liked it because it reduces the algebra that you have to do. So for a couple semesters, I tried to push it as my top choice. And what I found is that probably 60% of the students still like to use their algebra and solve. And just a small portion of people were comfortable using the concentration as a conversion factor. So now I'm just going to kind of present it as a side. And if you want to see other problems that way and you're like, I really want to know how to do this, can you help me? I'll help you. Individually or as small groups. I think it's worth taking a look at, and for some of you, you may find that this really simplifies what you're doing. It may be how you already think about it. So what we know, and what you would have to remember to start this, is that when we say a percent, it's out of 100. So when I say 3%, if it's mass to volume, what I'm saying is that I have 3 grams of my solute in every 100 milliliters of my solution. Okay, that's what 3% means, right? That you have whatever. If it was 10%, I would have 10 grams in 100. Whatever the percent is, it's always out of 100. And that is something you would have to remember to use it as a conversion factor. Okay, so this is what we're going to use as a conversion factor. Because anytime we have 2 different units that we can write as a ratio, we can use it to cancel other units out. And we can write it as it is, as I have here, or we can flip it. So the thing to do this, if you want to try this, you have to remember what a percent is. And a percent is that number, whatever the percent is that they give you, out of 100. Okay. So then this is how we would solve the problem. We never start with the percentage. That's our conversion factor. So that there'll always be something else given. So in this case, it's the 10 grams of our solute. This is given. And then we're going to use that concentration that I have up there. Because solute is given, I'm going to flip it. I'm going to put the solute on the bottom and the solution on the top. You see your grams of solute cancel, and you get the same answer. So I love it because there's not really any rearranging. I don't have to bring volume to the other side or do any of that. The key is remembering that percent is something out of 100, and then you use that with the other thing that's given. So you don't have to even if you don't want to do this, you're like, I don't even want to say the word conversion, then go back and use your algebra. It works every time if you do your math right. But some of you might think, I'm going to try that. And if you want to try solving problems this way, I encourage you to. Give it a try and just see how it goes. Okay, so I have one more. This also is going to be similar to what we just did. And so I'll solve it both ways again. So it says, what volume of soda that is 6% by volume alcohol contains 200 milliliters of ethanol? All right, so what have they given me? Let me change color so I can see. So they've given me, this is the concentration, and it's by volume. So that means it's the volume of the over volume. So it's going to be the milliliters of the solute divided by the milliliters of the solution times 100. So first we're going to do our algebra. And it has in it 200 milliliters of ethanol. So this is the solute. And they want us to know the volume of this alcoholic soda. I don't know how it's. I just copied this out of a book. So anyway, that's okay. All right. So I know the percent. So I know this number is 6, right? I know the concentration. I know I have 200. Oh, I'm remembering this problem now. We'll laugh at the answer. Okay, out of the volume here, and then times 100. So if I'm looking for the denominator, and they could ask you to find the amount of solute in it, so that would be the numerator, but this asks for the denominator. But if it's in the denominator, multiply it over to the other side. Then that will still have a 200 over here. Oh, I don't need the milliliters for when I solve it this way. Times 100. And then I need volume by itself. So I'm going to divide the 6 to the other side. Okay. I think this is going to be the same answer. Okay, or close to this, still the third. 3. 200 times 100 divided by 6. Yep, but it's 3,000. And again, with only 2 sig figs here, I would say 3,300 milliliters. Okay, so this is what I laugh when I read this question, and I obviously kept it in my PowerPoint, so I don't care that much, but this is like 3 liters of this soda. I'm thinking that's a lot. 3 liters of this, yeah, I don't know. Anyway, it would take 3 liters to get 200 milliliters of ethanol on that. That's a lot of soda. Okay, so now let's look. That was the algebraic solution. Let me just do this one also in using it the concentration as a conversion factor. So from the previous problem, I remembered that the concentration was 6% by volume. That's a concentration. And what was it? The volume of the solute was 200 milliliters. Okay. So if you were using it as a conversion problem, then what you have to remember, a percentage tells you how much. So I have 6, and this is volume to volume. So I have 6 milliliters of the solute over 100 milliliters of the solution. That's what a percent means. It tells you how much out of 100 you have. So I have to remember that to use it as as a conversion problem. And so then what you do is you always take what's given. Don't start with the concentration. So I know I have 200 milliliters of the ethanol, which is the solute. And so that was given. And then now I'm going to use the concentration. Now you do have to make sure your units cancel. So if I was given solute, the solute would have to go on the bottom. So I'm going to flip it. And so my solute cancels, and then I get my answer, which would be the same. So I know I kind of hyped up the conversion factor, but I want to tell you honestly, you don't have to do it that way. You can use your algebra. If you want to try things that way and you have problems and you want to ask me if you're doing it right, please feel free to email me or see me in class.